Good morning, everybody. All right. So I'll be presenting to you the kinetics of a proton coupled electron transfer from a tyrosine to an iron 4 porphyrin propionate substituent. So a little background, in my lab, Roger's lab, I research an enzyme called coproheme decarboxylase. And its function is to catalytically convert coproheme 3 team B through two successive decarboxylations of the propionates at positions 2 and 4. That's all I'll talk about right now. Here is a proposed mechanism for coproheme decarboxylase, and the interest of my research I'm presenting involves this step right here, the proton coupled electron transfer from tyrosine to the porphyrin ring through a propionate at position 2. So we generalized this model by just taking a porphyrin ring with an iron 4 and with one propionate substituent. And here I show how Dr. Han developed the potential energy surfaces for my potential model. And so he used molecular dynamics, specifically including the hydrogens here, here, and here. So those three, here's a little bit of a plot here. I don't have much to explain on this slide, but Dr. Han used these hydrogen-oxygen interactions to conduct a transition state search to form my potential. So these were the potential energy or the transition state barriers for my potential that Dr. Han generated. And I believe the potential I was provided with was a linear combination. Nope, we took the lowest energy transition state potential barrier for my model. And so the classical mechanics would dictate that the proton would transfer at 0.22 electron volts or 2,500 Kelvin. And the hypothesis was that our quantum calculations would yield lower activation energy and show quantum tunneling because we're below that 0.22 electron volts. So a little bit of an overview for the methods used in MATLAB code. First, a Hamiltonian operator was calculated with the sum of potential and kinetic energies. That was used to form an evolution operator, which was used to evolve the wave function of the proton through time. Temperature for the reaction could be calculated based on kinetic energy and the Boltzmann constant. And further, the Arrhenius equation could be used to calculate a rate constant, and a modified Arrhenius equation could be used to generate activation energy, similar to what Curtis showed and what James showed. So let's see. Here I'm showing a little movie of a proton wave packet with an initial temperature of 55.3 Kelvin. Kinetic energy with the parameter I changed in these experiments. We can see how it moves towards and across the potential barrier, with some of the probability distribution being reflected back while most of it makes it through and is transmitted product. Pretty neat. So I've conducted this experiment or this simulation at various temperature. All of them were done over 1,000 atomic units of time. And we can see at a low kinetic energy, the proton was entirely reflected back from the potential barrier. At about 50 Kelvin to 60 Kelvin, we see a mixture of reflection and transmission of the probability distribution. And at a high temperature, we get complete transmission. Here's a better representation of how the proton probability distribution moves over time. Again, we can see that the proton is reflected back from the barrier And then we get a mixture as we increase the initial kinetic energy until it is fully transmitted through the barrier. And all of this is well below the activation energy dictated by classical mechanics. So using my various simulations, I collected data, and here are some plots showing my percent yield versus kinetic energy, which is in joules, but this is from 0 to 77.8 Kelvin. And then I use the Arrhenius equation to plot the rate constant versus kinetic energy. And they both show a similar trend at about 50 Kelvin. They start to show an increase, a very steep increase, and then level off shortly after. And then I could use the modified Arrhenius equation to plot the natural log of the rate constant versus the inverse of temperature. And the goal of such analysis is to find a linear region and fit it to obtain a slope that is proportional to the activation energy of the transfer. So here I've zoomed in on two regions. That region is not very linear, so that's just to show that there's only this one linear region on the plot. And after obtaining a slope that is proportional to the activation energy, I could calculate the activation energy of 7.1 times 10 to the negative 7 or second electron volts. So, in conclusion, the potential energy barrier height of the transition state was 0.22 electron volts. But I showed with my quantum calculations that there's in fact an activation energy of 0.071 electron volts. So the quantum simulation for the proton coupled electron transfer from tyrosine to an iron 4 porphyrinate substituent yields 33% or less activation energy than classical mechanics. So this is really cool because it provides a base model for this experiment. However, it has the same downfall of Curtis's experiment. We don't actually show the transfer of the electron, just that of the proton. And we would also need to account for specific enzyme catalytic environments and an implementation of more complex and dynamic potential.